guys. In this video, I'm going to be doing just talking about space, astrophysics. I used to really want to be an astrophysicist, so I know a lot of stuff about this crap. I'm not going to bore you guys with the math. If you want me to talk about math, I can definitely do a video about that. But I'm just going to talk about cool stuff, talk about some of my favorite stuff. But anyways, so that you guys don't get bored, let's talk about magnetars. Okay, so these things, they're like big old stars, right? They're big stars, and they have these giant magnetic fields, that are hella strong, like probably one of the strongest magnets in the universe are magnetars. Currently, we know of 25 that are in our solar system. Or not solar system, oh my god. In our galaxy, we know of 25 that are in our galaxy. Also, a lot of this information that I'm going to be talking about comes from books. So if this information is outdated, then that's probably why. It's because all this information is coming from freaking astrophysics books written in who knows when. But anyways, yeah, magnetars. They are just giant balls of energy, pretty much. I mean, that's what most all stars are. But like these things are special. And the reason why they're so special is because of their giant magnetic field. Like, it is exorbitantly strong. Their magnetic field is so strong that they have this sort of like fluid on the inside. It's sort of like our mantle. It's sort of like our mantle that moves around on the inside. And then it also has magnetic waves that like screw with the. By the way, these things, there is so much energy in them. They have a crust. They are stars with a crust all around it. All around it has this big crust. Like the Earth does. I mean, not like the Earth, but you know what I mean. It has a crust on it. And then there's ooey gooey inside. It's magnetic crap. And I'm going to be using very simple terms because I'm not going to yap about, random crap, because I want all you guys to be able to follow. I'm not going to talk to you guys like idiots, but also I'm not going to talk to you guys like you'll know every word that I'm saying, because I want you guys to be able to learn. I want you guys to be able to know this stuff and impress people and be like, hey, I know about magnetars. I know about, I'm going to talk about, probably, gosh, what was I going to talk about? I don't even remember. It'll come to me in a minute. But anyways, yeah, it's got a crust on it because there's so much freaking stuff in it, or not stuff in it, energy in it. And if you want a reference for how much energy this stuff has in it, it has starquakes. It has so much energy and so much movement in it that is starquakes, and a little tiny crack in them that's only a few micrometers wide can cause giant starquakes and so much energy just spewing out of it. And these starquakes spew a lot of energy. There was a magnetar in our galaxy that had a starquake in it, and that starquake released so much energy that the energy that came out of it was equivalent to, in 1/5 of a second, it was equivalent to 1,000 years of energy that our sun produces. 1,000 years worth of energy that our sun produces, it produced in 1/5 of a second. And I'm going to get into an even bigger one. There was another starquake that happened in like 2004, I think. And it released so much energy that we felt it here. Like it was noticeable that it happened. Obviously not to everyday people, but like with our satellites, because it released so much just kaput, obliterated. Half the distance that it was away. If it had just, we'd be gone. Like, imagine if two of these things collided. Could you imagine the amount of energy that it would put out? Now, obviously, the chance of that happening is astronomically low because these things are very rare. In our entire galaxy, we only know of 25. But this looks like a whole bunch of jumbled mess. But anyways, yeah, magnetars are pretty cool. They are pretty insane. What else? What else can I talk about? What else can I talk about? I feel like there's more about magnetars that I can talk about that I'm just forgetting right now. They're a type of supernova, or not a. You can say they're a type of supernova, I guess. It's yeah. Anyways, let's talk about supernovas actually. So supernovas are these giant, extraordinarily dense stars that are just like, I mean, I you know what a supernova is. It's a super cool blue star, pretty much. And the reason why they're so powerful is because they have so much freaking density to them. They have so much freaking mass. It has so much mass that as they age and they're God, that is the worst arrow I've ever put in my life. As they age and their little body starts to grow out, the mass of all this, which is pinpointed like right here, it's like, hey, I don't really want to expand. I want to shrink. I want to get smaller. I want to go towards that point. Oh my God, these arrows are so good. I want to go towards this point. And now, because these have so much mass to them, the atoms on the inside are like, hey, no, we don't want to touch each other. We don't want to be close. You need to go out. You need to go out. And so, depending on how much mass it has, either the atoms like, hey, stop, go away, and this all just kablooey, and then big explosions and super bright light and a bunch of stardust everywhere. And then usually, or wait, I'm explaining this very poorly. I need to explain like how the actual process of that is. So what it is these are like, hey, stop, and it starts pushing out and pushing out and pushing out and pushing out, and then eventually all that matter is like, hey, no, and it comes back down and slams into that core and bounces off the core and just boom. So it's not like it shoves it out. It's like it gets pushed out by the atoms, and then it gets far enough out where it all collapses back in because it falls under its own gravity, and then bounces off its like super dense core, which is usually iron. It usually has a core of like iron or something like that, and it just bounces off of it. Or what happens is there is so much mass that it just keeps on crushing and keeps on crushing and keeps on crushing, and eventually the atoms will start to melt together. Not melt, but you know what I mean? They start to get squished together, and you'll have what it looks like. They call it atomic lasagna because that's what it looks like. It looks like that. It starts melting together. Or it'll be a more hexagonal shape. I don't want to draw this, but it's very hard. Basically, the circles are hexagons. Just imagine hexagons. And they are in like a crystalline structure pretty much. And they're all like melted together. Because they're being forced together. They're being forced to touch each other. And in situations like that where these atoms are being shoved together, there begins to be so much stuff there that as space, going through space, going through space, going through space, and then it hits that part of the sheet and just sinks. And that's why it can't escape it. But if it's like, on a different level, if it's far enough away pretty much, instead of getting sucked into it, it'll just bend around it. That light will bend around the black hole. And that's why with black holes, what you'll see is you'll see these sort of, here, I'm just going to turn this into a black hole. You'll see these big, like circular shapes around it, because what's happening is like light and stuff and different stuff like stardust I'll use. It's just, instead of getting pulled into it, it's orbiting it pretty much, because black holes, some black holes spin really fast, not all of them do, but what's happening is they orbit it, and because that pull is so strong, it's always speeding up that stuff, speeding it up, and it creates this bright light all around it. So that's why they look like that, because all that stuff is spinning so fast, it begins to like, I mean, the light too, the light is also like coming off of it, which, you know, they say nothing escapes a black hole, but the thing is, they're not at the black hole, they're orbiting it. It's just going around the black hole. It's not actually doing anything per se, or it's not actually going into it. And something really cool is with black holes, they'll actually have these cones on the poles of the black hole where there's radiation being shot out from these big cones on the sides, or the poles, where radiation from all this stuff spinning so fast, spinning faster and faster and faster, that it just from the poles, or not, it's more like a beam, pretty much. All this stuff just shoots out like a beam of radiation. And also, you've probably seen like black holes are a portal to another dimension, or they're wormholes. Well, we can prove that they're not because of Hawking radiation. Whatever goes into a black hole, we can see that it comes out of the black hole through Hawking radiation. So like that radiation comes out, and it's the same information of stuff that went in. So like, if we had something that could read Hawking radiation and tell us what it was before it was spaghettified, like if a person went into a black hole and then he came out as Hawking radiation, if we had a machine that would take that information, this box is the machine, or I guess triangle, if we took that information, put it in the machine, we would get the information for that person, because it doesn't delete it, it doesn't like keep it, it over time will put out the radiation, the Hawking radiation, as the information for whatever it took in. So now it's not a wormhole. You won't get sent somewhere. You won't go to another dimension. You'll just be spaghettified and then shot out as a bunch of radiation. But anyways, back to what I was talking about. These things are really weird, because instead of like bending space and time, it's like pulling it in. It's pulling in the vacuum pretty much, and compacting the fabric. So it's like, instead of being like that, or like that's so bad, it's like that. So this would be that, but all this right here just got shrunk into that one little area, and that's what these are. They're just places where the space-time or where the vacuum of space just shrinks space is pushing in, these super thin walls, which are like I said, make atoms look massive. They are incredibly strong. And were you to touch one of these, you would just dissolve pretty much. You would just disappear. And you would become super dense nothingness. You would become part of this. And it would just ever so slightly grow. But yeah, very cool stuff. What else? What else? Let's talk about. What do we talk about? We should talk about. Let's talk about how space is always moving. So it's not moving. So a multi-galaxy traveling species is pretty much impossible. Honestly, solar system to solar system is pretty impossible unless we find a way to like freeze humans to a point where they don't really, or they're like perfectly preserved. The reason for that is, as the universe, hold on, I gotta do it from this side. As the universe expands, the atoms really want to expand. Atoms really want to grow further away from each other. So as the universe expands, the atoms in the universe more and more want to grow apart. They want to go away from each other. So in like a billion, trillion, whatever years, eventually theoretically something called the Great Rip will happen, where there'll be so much space that all the atoms will grow further and further apart from each other, that nothing will be able to exist. This is all theoretical, but it's on paper, it works. But anyways, so what was I talking about? Yeah, the Great Rip. But anyways, so like this galaxy right here and this galaxy right here are also growing away from each other. They're also growing away from each other. And the issue with that is because the space between them is growing further away from each other. They're not moving, but the space is growing. So it's like how do I explain it? I mean, I'm sure you guys understand, but there might be some people who don't. I can do it with my wallet. So think of the 2 points on this wallet. These are 2 galaxies, right? And now these galaxies are stuck in space. They're right where they are. Now, they don't move at all. They stay right where they are. But the space between them starts to grow and grow and grow. And so they don't actually move. But the space between... Sorry, my phone ran out of storage. But anyways, so yeah, the space between them is growing. And I know that for some people that might be a little bit like hard to comprehend. But like, I mean, that's what's happening. Like I said, space isn't empty. It's the fabric. It's like a fabric, pretty much. It is something. It's just not something we can really like touch or feel or anything. But it's there. Like where there is nothing, it is something. Nothing is something. and that something is always growing as the universe grows. And sorry, I have to see my freaking mannequin over there. But yeah, it's always growing. And now you can't really notice this or measure this unless you lived for 1 trillion years. Then you'd be like, oh yeah, these have kind of moved away from each other. But anyways, the reason I'm saying that space travel across galaxies, all that is impossible pretty much, is because the space between this galaxy and this galaxy are always growing, and because we can and like if humanity could make a way to go the speed of light, a lot of these, the space between them is growing faster than the speed of light. Now that may cause some misconceptions. Like I thought nothing could go faster than the speed of light. It isn't. Nothing is moving. Oh my god, those birds are so loud. Okay, sorry, we're back. So, even if humanity could go the speed of light, a lot of these things are growing faster than that. Which means nothing is moving faster than the speed of light. Still, nothing can go faster than the speed of light. But the space between them is being created faster than light can travel. So there's also places that we will never be able to even see because the light will never get to here. Bro, that freaking bird. Okay, we're back. I hope this is the last time. Yeah, we will never be able to even see them because the light between them has grown. The space between them has grown so much more, or so much faster than light can travel it. And the only way we'd be able to see other galaxies pretty much is through wormholes, which we are yet to see them or see any proof of them from what I know. But anyways, yeah, session over. I really appreciate you guys coming. If you guys want more space stuff that I can talk about, oh my god, that bird, don't start. If you want more space stuff for me to talk about, or if you want me to talk about more space stuff, or you have something specific you want me to explain, let me know, and I will be sure to make another video because this is like only a quarter of my thing. There's a lot of paper on this. But yeah, I will be sure to explain whatever you guys want, talk about whatever you guys want, because I love space. Space is awesome. It's so interesting. But anyways, I will see you guys in the next video. I hope you all have an amazing night, amazing day. Be sure to subscribe, please, because I know I have to say it because I'm a smelly, stinky YouTuber. But anyways, I will see you guys. I hope you have an amazing day. I hope you sleep well. I hope you have amazing dreams. And yeah, see you all.